Okay, so this is quiz number 2, problem number 1. It is the same on both forms. So, we want to determine where the function of the following graph is continuous. So I want to find where. Alright. So, remember, continuous means the limits are equal to the function at a point. So, if I look at this, at first glance, two things jump out at me. First is x equals 1, second is x equals 0. I got some open closed circle stuff going on. I should probably check what's happening there. Everywhere else, well, if I start here, I can draw this part smoothly. I can draw this. I can draw this. So I don't really need to worry about those. Okay. So I should see what's happening at x equals 1, what's happening at x equals 0. Alright, so let's look at x equals 1 first. Well, if I approach this from the left, follow this line in, the limit of f, we're going to refer to this as f, like we always do, as x approaches 1 from the left, it's 1, right? I'm on the left side, I'm approaching x equals 1. Well, this line is going to be approaching this point, this open circle here. Same thing on the right. It's going to be approaching the same open circle. So it's equal to the limit of f as x approaches 1 from the right. Okay? There it is. So, limit as x approaches 1. So the limit exists then. Limit from the left equals limit from the right. Limit exists. And it's just 1. So the question is, I want to check, is this the same as the function at 1? Well, if I plug in 1 to this function, I go here, I've got an open circle and a closed circle. Well, f of 1, this closed circle means is going to be this value. You always go for the closed circle for wherever the value is if you plug in 1 to this equation. So, let's see, f of 1 is here, it's negative 1. Oh, 1 is not equal to negative 1. I'm discontinuous at x equals 1. Oops. This is f of 1 up here. So discontinuous at x equals 1. Alright. So now I want to check over here at 0. So I'm going to approach from the left. Approach 0 from the left. So I'm going to follow this line over here, and it's going to go to this open circle here, which is at negative 1. And now I'm going to check, so is that equal to the limit from the right? Well, the limit approaches 0 from the right. Well, I'm going to take, here's 0, so I want to be a little bit to the right of 0, so I'm going to come in this way. So I come in this way, and I'm going to hit 3. Alright, so this line over here ends at 3. This one over here ends at negative 1. Uh-oh. Those are not equal. So limit at x equals 0 does not exist. And if the limit doesn't exist at a point, well then, it's not continuous at that point. Alright, so we're discontinuous at x equals 0 and at x equals 1. Well, if we're discontinuous at x equals 0, x equals 1, take a look at everywhere else. Well, I'm continuous over here. I can just draw this, right? It's a nice smooth line. That line is continuous, that line is continuous, but 0 and 1 I'm not. So, where am I continuous? I'm continuous for all x not equal to 0 or 1. Alright. Now, if you're given a graph, not all of this is necessary for explanation, for the record. One could look at this and say, well, here, I've got an open circle here, and then a closed circle somewhere else. Well, anytime you've got that, it's not going to be continuous to that point. So you can just look at a graph and say, I see an open circle over a closed circle. Well, that means I'm going to get here, I'm going to have to jump. It's not continuous. Right? I have to pick up my pen to graph this point and then come back here. Same thing over here, I can graph this point, and I have to pick up my pen to graph this over here. Or go the other way, I have to pick up my pen. So open circles over closed circles are always going to be discontinuous.